everybody. So today we're covering plane strain, and I thought I'd just give a little bit of an overview on this topic to supplement what you have. It's not a topic that everybody spends a lot of time on, shall we say, in terms of mechanics and materials. And it's a little tricky, but it's not so bad. So the first thing about plane strain is, what does it look like? Okay, that's kind of my question. And if you've been doing these problems now, you're like, oh, the math is not that bad, right? I just use the equations, but it's also kind of nice to be able to have a visual. Okay, so I think people kind of understand what epsilon x, epsilon y look like by now, right? You're pulling out one side, you're pulling out the other side. But just kind of a general way to draw this to line up with rotation and what we're seeing is kind of as follows, right? So if I have a state of stress on an element that's resulting in a strain, or if I just have strain on an element, okay? What I would say is, okay, this is the base element, right? And we can say maybe that we have an x direction and we have a y direction, like so. And the thing to do to kind of draw it out to capture the shear strain is kind of just make another diamond. Okay, so you can just draw like a few points, kind of like this, 4 points, okay? And then you just draw between these points. Okay, and this is not perfect. Okay, as you know, I am not, for sure. Okay, but this kind of gives us a general depiction that we can then use to talk about the strain. So if I'm interested in talking about the strain in the x direction, okay, what I can do is I can relate it to the displacement. Okay, so I can say that epsilon x dx. Okay, and if I'm interested in the strain in the y direction, I can write epsilon y dy. And if we're interested in the shear strain now, okay, that's the one that's a little more confusing. We have multiple options to choose from. Okay, so one option is to say, I'm going to use this theta inside, and I'm going to say that gamma xy is equal to pi over 2 minus theta. Okay, and that is kind of what we discussed, I think, in the second meeting, third meeting, maybe it was the fourth meeting when we fourth meeting when we discussed stress and strain. Okay. The other option is to simply state that it is in these regions and that it is the gamma xy over 2 in those two regions. Okay, so that if I had an alpha, if I have an alpha and a beta, okay, that gamma xy will be equal to alpha plus beta. And typically when you draw these out, alpha and beta are going to be equal. Okay, so that's kind of how this is maybe just some tips in terms of how you can go about drawing plane strain in a reasonable fashion. Now, what happens when we rotate it? Okay, well, the same kind of thing is going to happen as we've seen prior. Typically, we're talking about counterclockwise rotation. Okay, so I come over here and I'll say, well, let's just tilt my square, and I might have some, maybe we'll use black. Okay, so unfortunately I use theta. This is what let's just say the rotation in this case is phi, okay? I know that's not what we often use, but let's just say that we rotated the element phi. So in this particular case, right, what we can kind of go by is the original x and the y, whereas we see there, okay? And now the new x prime and y prime, right, are as we see there. And when we go ahead and we draw our diamond, okay, once again, we can kind of come out here, and we can come out here, and maybe here, and we can go ahead and draw it like this, okay? And in this case, whoops, I missed one, okay? We'll do it with this color. No, we'll do it with, yeah, we can do it that way, I guess. Just make it a little smaller. Let me, just make it a little thinner. Okay, so here, this one right in this region, that's going to be the epsilon x prime dx prime. Okay, and in this over here, we have our epsilon y prime dy prime, like that. Okay, and once again, the angles in here and here, those are going to be the shear strain divided by 2. So that would be a gamma x prime y prime divided by 2 out there. And that's pretty much it. So that's how we go about plotting these. Oh, there is one other thing. If you think you have negative shear strain, right? If the shear strain is negative, is less than 0, then we actually have a fun situation where when you're drawing your modified diamond, that doesn't look good at all. Oh, that was like the worst. Still not very good. Okay, that's pretty bad. But anyway, it's not a nice looking rhombus. But anyway, so in this case, right, this would still be gamma xy, right, over 2, but this is now negative, right? This is going to be less than 0. Okay, because it's gone beyond the 90 degrees. Any questions, thoughts? Okay, yes, Robert. Oh, Tyler. So the question is, how do you relate the x prime and the y prime? Oh, well, the x prime and the y prime, I mean, I think one thing to keep in mind is that we're dealing with 2 reference frames. We're dealing with kind of our base xy plane, right? And then we're dealing with a reference frame on top of it. So before we even do anything with stress or strain in these cases, what we have, at its root, we have, a reference frame that looks like that, and then we're putting on top of it another reference frame like that. Okay, and then we define, in this case today, we're calling it phi, okay, which is not, normally we call it theta, okay, but then we have the angle rotation between them. Oh, epsilon x. Okay, so epsilon. How do these relate? Okay, well, what is what is epsilon, right? Epsilon x, right, or an epsilon is going to be equal to a change in length, right, over the original length, right? Or maybe it's a delta dx, right? But that's a little bit repetitive. Okay. So if we then say that this thing right here, right, that region right there is epsilon x dx, right? So epsilon x dx just becomes the change in the length, right? So that's really what we're that's what we're talking about right there. That's a change in length, right? And but I know that epsilon x is essentially well, it is this change in length over the dx. Okay, was that helpful at all? Okay, good. Thank you for asking. And I'm sorry, Robert. Okay. And then you said, Alex, there was a typo. I had some x primes and y primes when I should not have x primes and y primes. So let me go in and I'll fix that real quick. Oh, there's something in the group me. Yes. Yeah, right. So that, Chris, I see you online, or I see your comment. That's exactly what Alex was saying. That I put a typo. We need to be, so if we go to, this is for questions 2 and 3, if I'm not mistaken. Yeah, so we're using a gamma xy here, okay? So I'll reflect that. I just got a little bit happy in Canvas. Okay, and then question 3 also needed to have some adjustment. Canvas is interesting in that it uses so you've probably some of you are familiar with LaTeX. It doesn't use LaTeX exactly. It doesn't use the dollar signs. It uses this interesting slash parenthesis. So it's a little bit different, but the once you have the slash parenthesis, it is the same. Okay, so those should be updated. Good. I'm glad people are on 2 and 3. Okay. And then the other thing that's kind of cool about this session is that we're learning how to measure strain using strain gauges. And I guess hopefully it's somewhat explanatory, self-explanatory in in the slides and in the posted video. But essentially, we have like the point right of these strain gauges is that they measure in one direction, and we need multiple of them to measure the three components we're interested in plane strain. So, right, we're interested in epsilon x, epsilon y, and gamma xy. So if we were to put them all in a row with the same orientation, or not even in a row, if they just all have the same orientation, they might all pick up that one direction. Okay? And that might be good if you have some issues with your accuracy, but by placing them at angles relative to each other, and they don't have to be, at 45 and 45 or 66, right? They just need to be at different angles. Of course, you might have some issues with sensitivity if you all do like 1 degree, 2 degree, 3 degree, right? You're gonna have a lot of noise that you pick up. So putting them at 60 degrees kind of lets you get that nice even spread over the range and distributes the amount of uncertainty that you might have. Anyway, so it's kind of a nice addition, so that when you go and you instrument an object with strain gauges, you can figure out what that state of strain might be. Has anyone used strain gauges before in this? Okay, so our lab has worked with strain gauges a little bit. We've made some wireless ones where we're attempting to measure a change in electrical impedance. So, in the slides we call it resistance, but we were actually looking at systems where we have AC current that we put in a coil that then gets transferred through induction to another coil, okay? And then it runs through an element that is sensitive to strain. And then we pick up that impedance, those changes in impedance, right? So, for example, if you have a pressure vessel, and this was kind of work we were doing for aerospace applications. You have a pressure vessel, and you want to know what the pressure is inside. Okay, you have a couple options. One is you could attempt to measure the strain on the outside, right? Or the other would be that you have some type of element that can handle and measure the pressure inside the vessel. But you don't necessarily want to run wires through. You don't want to drill holes in your vessel to get the wires in. So the idea is how can you measure the pressure inside, or how can you measure strain inside the vessel or along it without using wires to get to it? And on top of that, so then you're like, well, if I don't have wires, do I need a battery, right? Do I need a battery on that sensor? Well, if you can use inductive charging, okay, it's possible that you have a passive sensor element that you then ping with current, okay, or with a magnetic field, essentially. There are other systems where they do have like a little capacitor or a little micro battery that will scavenge energy, all right, from its surroundings, and then every now and then send a signal back. So imagine that you have an interrogating signal, and it picks up this energy, and it charges up, saves it up, and then it says, "Boop! This is the measurement." Like once, like 0.01% of the time, or something like that, right? So that's another strategy that people have been exploring for being able to report strain measurements or other measurements, temperature measurements, whatever they might be, wirelessly. Okay. Of course, you can always have batteried sensors, right? But if you're putting them on wings or other objects, you don't necessarily want all that weight and all that mass and all that bulkiness. Or like one of the dream applications is that you would be able to sense and have embedded sensors on wind turbines or jet engines, right? On those blades that are very susceptible to breaking, okay, and strain and cracks and things of that nature. So if you could somehow have a great sensor on there with that's super lightweight and it's not going to affect the structural properties and the strength, but be able to tell you what the strain is in real time, you would be able to avoid having to do all the inspection that you typically have to do. Okay, great. Thanks for listening. I just went off. Strain sensors are cool. Okay, they are. Johan? Okay. All right. Yes. Yeah. So why don't we do it by load? Does that make sense? So let's start. I mean, I think like here I would write, okay, these are the PX ones, these are the PY ones, these are PC ones, right? Okay. So which one is so just like which one are you focused on right now? Mhm. Okay, so the difference between a normal stress and a shear stress, right? Yeah, transverse shear stress or twisting or torsional shear stress, right? Okay. So why don't you go to the beginning of this, where we outline all the different loads that we have? No, not this. The very beginning of these slides. Why don't you just download the slides to the bottom? Right? No, not that. Not that. That one. Yeah. Okay. So if we go right down there, okay. So these are our options. Okay, these are all the options that we've covered up until this point, right? We have normal forces, shear forces, bending moments, torsional moments, and thin wall gusses for their normal stresses. Okay, so uh, we want to go through. We can go through each of these maybe before we even do this. Okay? So this one, tell me, all right. First of all, these are normal stresses, right? Which classes are those? And what you just saw. These are all the options you have. So which ones are these? Sure. Yeah. Yeah. That's the easy one, right? Yeah. So I usually say moment. I say, I mean, torques and moments are essentially, yes, very, very similar. But when we talk about beam bending and we talk about the normal stresses, the bending stresses associated with beam bending, we usually refer to them as moments. Okay, so yes, that's a moment, right? And so the reason that's happening, right, is because that is offset from the center. Okay. Okay. So then you draw the other part. You draw the. Okay, that's fine. Yeah, yeah. Okay. So now, so maybe pull up the other thing that you had. Or, you can just go to the slides. We can just stay in the slides. We don't have to jump to different parts of the video. Just, Yeah, that's what we're trying to do, right? At least we force it. But yeah, we didn't, so I didn't draw any torques here, right? But the forces are resulting in torques or moments. Okay, good. Good, good. Oh, okay. Yeah, yeah, yeah. No, 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 no. Hold on. So this is yeah, I should bring this under. Right, because there's a two over here. Right, so m divided by 10.
I run through this fast.
I agree with you on that. Well, hold on. So this is positive. So you should be correct. Yeah, that was Can you guys save these things? Well, they're just yeah. I mean, right, so that's like, so I looked because I knew you all love it. So I looked into it, right? So I just got the I couldn't figure out how to say it. Yeah,
Oh, shit.
Oh, okay. So in other words, when you do these, you don't you just get rid of the physics because it's all microstrain, right? They typically say 10 flex strain, 20 microstrain, and the end origin is so you still have to. I mean, you don't really have to convert because you can just as long as you keep everything, as long as it's like, yeah, I know this is microstrain, this is microstrain, this is microstrain. You, it's like you're essentially multiplying the whole equation by times right? So then everything just comes out. Yes. Okay. So, no, this is important, right? So, the, let me just pull up my notes there. Okay. So,
Since there's no in-plane shear strain for the XY, the XZ plane,
so here we're talking about plane strain 20, 15, and then gamma, right? Yeah. Okay. So,
and then it also gives epsilon z as 0.
yes, correct. Right. So, what do you do with that?
Since there's no in-plane shear strain, it would be epsilon x divided by 2 since it's the northern of the 2, right?
Okay. So, yes, the epsilon x is all the way out on the right, correct? Okay.
And then dividing that by 2 gives the radius of
Right.
one circle.
Right.
So we tried that.
But then but if the radius is equal to what?
The maximum shear strain.
Right? And the shear strain on the y-axis is in gamma xy divided by 2. Right? So that's the
Okay.
kicker. That is the kicker. So
Okay.
what is it going to be?
Epsilon x, right? Okay.
Because you have to multiply by 2. So what does that mean? It means that the maximum shear strain is the same as the maximum
Okay.
principal stress.
Okay, that makes sense.
All right, that's kind of wild, right?
Yeah.
Yeah. It gets me every time, or maybe not every time, but it's like, why does this happen? Why does the physics work this way? Why is there this gamma xy over 2? It just does.
That's a little mind-boggling.
Yeah. Okay. Good. But that should solve it.
All right, thank you.
Mm-hmm. As if it's cylindrical, yes.
Right.
Yeah, we derived it in fact. Well, take a look. It's in there. Yeah. It's under the transfer shear stress lecture or set of notes. So if you go up, yeah, that one. Beam split. Keep going down. Going down. It's interesting. You like went to the videos. I'm like, I'd rather go to the slides. That's fine. It's just interesting. shear stress is along the longitudinal axis. But if I take an element, right, that is on the longitudinal axis and on the face, so I take a slice, right, they're on the same element. So they're the same. And the transverse shear stress on that face ends up being the same as on the longitudinal axis, or on the longitudinal direction. It's larger when it gets to the neutral axis. It's maximum. Transverse shear stress is the max of the neutral axis. Because you have all that A prime. Yeah, you can go through these, but remember that right, when like if you look at the basics, not basic, I shouldn't say that, the first derivation, go up to 250. Okay. Yeah, that one actually is pretty good. Okay, that's not. Do you see what we're doing? We are looking at a shear stress that balances against these bending stresses. And so if you're at the bottom, which is at the neutral axis, right, you have all these bending stresses that are that you're fighting against, okay, or that you're balancing against. But if you're at the top edge or the bottom edge, there's nothing there to balance. All right, because there's nothing. It's just air there. So the transverse shear stress ends up being 0 at the top and the bottom, and it's max at the neutral axis. Good. I'm glad you're asking. These are great questions. Oh yes, Anisha. Yes.
For question 3, do we use principal strain for the strain
Yeah, it should be. You're going to use physical strain.
So we can use the principal strain from the XY plane and apply it to the XZ.
Yes. It's essentially the same problem twice with a different wording. Well, and different physical significance as well. Okay? So, okay, so there's a question about question number 4. All right? So we have. Oh, it's time to go, actually. Oh, you all are so nice. Do you have fewer places to go nowadays? Kind of. Okay, that's a loaded question. All right, so here is the pressure vessel, and it's hollow, of course. And what we're saying is that we have our strain gauges A, B, and C, okay, in the rectangular rosette formation. And if I'm not mistaken, I think I said that the hoop, so if we have an element here, it doesn't really matter where it is, right? But this is going to be the longitudinal direction, right? And so this is kind of like a sigma A, okay? But it's I should actually probably be more careful. We're doing strain, so we'll say there's an epsilon A, okay, in that direction, and we're going to say that there's an epsilon C in the longitude and the hoop direction, in the circumferential direction, right? Okay, so where is, you know, these sensors? Where are they, right? Well, one is, if I break it down, right? One, the A direction is like this. Right, this is sensor A, and the C one is kind of like this. Okay, that's the C, right? And then the B one is at 45. Okay, like this. Now, you already have the equations for epsilon A, B, and C. Okay, right? We already have. Where is my mouse? Here it is. Right, we already have the equations for epsilon A, epsilon B, and epsilon C, and we know that they gave us, right, epsilon, or I gave you epsilon, essentially epsilon Y and epsilon X. Okay, or I didn't give it to you. You have to calculate it out, all right? And so if we have epsilon X and epsilon Y, we can figure out what epsilon B is, just because the gamma XY is 0 in this particular case, right? The gamma, because there's no, it's a case with principal strains, principal stresses, okay? So the trick is to try to figure out what epsilon X and epsilon Y are. So to do that, right, what we want to do is figure out, you know, the PR over T for the hoop stress, and the PR over 2T for the longitudinal stress, right? And then we can plug those in here, right? We have relationships, you know, in one case you'll have PR over T and PR over 2T here. In another case, there'll be a PR over 2T and a PR over T. Okay. So we figure out what those epsilons are, the epsilon X and epsilon Y are, and then we can plug them in to, not this one, because that's 60-degree one, into this equation, and that's what epsilon B is going to be. Okay, did that make sense? Is that helpful? I hope. Yeah. Okay, thanks for coming, everybody, and I look forward to seeing you on Friday.